And hello everyone again. Welcome to this update video of Turbulence modeling. So I've been off for like a month on hiatus and just wanted to explain where I'm at in terms of trying to get this DNS to work. Okay, so I've actually, as you can see, I'm not using Windows as much anymore. I'm actually using Linux Mint, and the reasons why I actually talked about in another video series about Linux Mint. You can search it out on my channel, but I like the experience a lot more. But I'm not using Microsoft Word or anything anymore, but I'm using LaTeX now to produce such documents like this, and all of this is uploaded onto GitHub. Okay, so my LaTeX files are there. You can go and take a look at it yourself. So what actually happened? I found that I ran into some bugs and I wasn't able to resolve them yet, and this was actually taking a lot of time. So I could not figure out what was going on. So let me run you through where we were. We were talking about Reynolds average Navier-Stokes simulation. That went well, and also the IDDES, the improved detached eddy simulation. Improved delay detached eddy simulation, that also ran well with a coarse mesh. However, when I try to run the summary is when I try to run things at DNS resolution, we have a very fine mesh, or LES resolution, where I have delta x plus about 40, delta z plus about 40, delta x plus about 20, give or take. It would still have instabilities and it will not solve. It could not resolve my turbulence well, especially for buoyant pimple foam. I was wondering why, and I spent a lot of time trying to debug this thing, and to this day I have not been able to get a stable resolved turbulence simulation running. So for RANS and the coarse mesh IDDES, it was okay. It basically modeled a lot of the turbulence, almost like Reynolds average Navier-Stokes method. So the mesh was so coarse that it basically behaved like a RANS model. There was no resolved turbulence. Okay, so let me run you through where we are. Okay, I have a first run of quasi-DNS. Okay, this actually was when I tried to have about 232 million cells and my whole computer froze. Second run, I tried to get my quasi-DNS to be a little bit more bearable on the computer. So I actually calculated what my smallest cell was in terms of Y+, and I tried to make the mesh a bit coarser so the computer can handle. And even that actually reduced from 232 million cells to 9 million cells. Still could not run. The whole computer froze, even doing block mesh. Third run, I actually reduced the cells further to 3.9 million cells. This was a DNS with no turbulence modeling whatsoever. It was about 3.9 million cells, and this was actually just barely okay for open foam. Okay, this is the limit that the Windows computer can take. Maybe in Linux, 3.9 million cells will be better because Linux is way more efficient. Linux Mint I'm using. It is way more efficient at handling RAM and everything else, so that should be better. But in Windows, Windows is just not so good for this stuff. Okay, so this was just for LE. This is just me comparing how many cells there are for LES in the X, Y, and Z direction. LES is a lot less. Okay, the mesh is coarser, and RANS also a lot coarser. So I calculated scales and everything. Okay, and I realized that I can actually have 3.2 million cells after all of this. So this is the absolute lowest number of cells I can take based on the delta x plus and delta y plus to resolve Kolmogorov scale. Okay, so when I try to do that, I reduced the number of cells to 3.2 million cells. I find that this is basically the upper limit of what my computer can take using a Windows operating system. So with the Windows operating system, about 3.2 gigabytes of memory will be used. The rest will be used. The rest of this 8 GB of RAM is used for all the random stuff that's being used in the background, which I really don't like. Therefore, I kind of switched to Linux because it was so much more efficient. So I realized that hey, even at this pace, it will take about a year to finish all of these for this time at this time step, and to resolve DNS, it will take about 1 year to get all the calculations out right. And even for this is for 100 seconds of simulation time. Even with 40 seconds, which is just barely enough, it will take roughly one entire university semester or half a year. Okay. So one thing I found out was that this issue crops up. It does not the simulation did not resolve the turbulence well. Only the coarse mesh LES and RANs works. Any smaller, the mesh size, when you reduce it to become smaller, it becomes unstable. So I begin this debug process of why is this instability happening. So one of the factors I thought was that hey, maybe the oscillations are too much, too many. There are too many oscillations there. Therefore, I have to use some turbulence model to try and control to increase the turbulence viscosity, so that the mean resolved velocity that will become more bearable to handle. Now, even with that, when I introduce a large eddy simulation model into my DNS kind of simulation with buoyant pimple foam, the whole thing blew up again. So I tried a bunch of other things. For example, increasing the number of and outer correctors in the pimple loop to stabilize the system, and even use with a linear upwind scheme. So this scheme is not a central difference scheme, and I talked about central difference scheme is like kind of a little bit more unstable than our upwind scheme. Upwind scheme is more diffusive. Okay, so it will not be as accurate, but it may be better for numerical stability. Now again, this thing failed. It failed pretty miserably. Okay, it just failed. So that was even trying these and outer correctors in FV solutions. Okay. If you know OpenFOAM, yeah, we have FV schemes and FV solutions inside the system file. So FV solutions, I tried tweaking these things here. I tried tweaking the and outer correctors here. I changed it to 3. I changed the discretization scheme to linear upwind. Okay, FV schemes. So this is the discretization scheme. I tried to make it a linear upwind, but by changing all of these things here, it didn't really work. Okay, so what's going on? I really don't know. I suppose that if your mesh is so small, K omega SST IDDES actually tends towards DNS kind of thing, so it just blows up. I tried. Another thing is to eliminate solvers as a problem in FV solution. So the solvers are over here in FV solutions. Okay, the solvers are here in FV solutions. I tried to change some of these. So for example, this PBICG, this is a precondition biconjugate solver, the stable ones. I tried changing it to Gauss-Seidel and other forms of smaller solvers, smooth solver in fact with Gauss-Seidel in FV solutions, because this was used in the DNS form boxtype 16 and it worked for that. It worked for that simulation. Unfortunately for this simulation, it just didn't work. Okay, the solver blew up. Now, okay, I noticed something. When the time step becomes small, the solver becomes unstable. That means if you have a time step of 1 times 10 to the minus 5, 1 times 10 to the minus 6, 1 times 10 to the minus 9, the solver tends to blow up. Okay, there's something wrong that happens. I don't know why. Okay, it seems to be the case. So I try to fix the time step rather than get it to adjust, because when your Coulomb number increases, and you run this adjustable time step in OpenFOAM. Okay, if you take a look at control dictionary, if you try to run this adjustable time step in OpenFOAM, and you see this adjustable time step, yes, in OpenFOAM, that actually causes when your cron number increases beyond 0.5, the time step adjustment will, OpenFOAM will try to reduce the time step. So when it becomes really small, when the time step becomes really small, the cron number, will explode anyway. So the solver becomes erroneous. Now, if I try to fix the time step, for example, if I try to fix the time step, I try to fix the time step, the instability still happen. I don't know why. It will just blow up. Okay. So I tried GAMG matrix solver in FE solution. Again, it didn't work. So this one, too small time step. I tried to change the time step with various solvers. Didn't work. I noted some interesting things here where K and omega actually reach the max iterations. Okay, so when buoyant pimple foam runs, the K and omega calculations actually reach the max iterations, and we have issues. So I wonder if that is the cause of instability. I turn off the turbulence model. Again, it was unstable, the solution. Okay, so once I was done with FE solutions, I turned to FE schemes. So I tried Gauss upwind. It didn't work. The Gauss upwind scheme in over here. I have this Gauss upwind scheme. Alright. I tried a lot of Gauss upwind schemes here. Didn't work. The solver blew up. Crank-Nicholson time schemes in the DDT schemes, cause apparently people say it was more stable. Again, didn't work. So this was the what do you call that? But this was one, actually, there are a lot of people who say that they run into this problem with buoyant pimple foam. I'm not the only one. So there are people online who have the same problem, and they try to use these things here. Okay, so maybe what do you call that? Maybe the schemes, the FE schemes was the issue. I tried to adjust it, but it didn't work. So I tried tweaking a lot of FE schemes. It didn't work. Okay, so perhaps mapping fields from a cost solution cause it to blow up. Meaning to say, I take for example, the IDDES case 1, it had a cost mesh IDDES, or I take a RANS simulation, Reynolds average Navier-Stokes, and I try to map that to a fine mesh. Okay, so that means I take that initial condition, the initial guess, to be that coarse mesh solution. So for example, I have a RANS simulation with a very coarse mesh, maybe 16 cells from one end to the other, and I try to use that velocity profile to be my initial velocity profile for, let's say, a mesh with 169, or rather maybe 36 cells from end to end. I'll extrapolate or interpolate the velocities onto this 36 cell mesh. Okay, so doesn't work, blew up. Someone thought maybe this dp/dt term in buoyant pimple foam actually causes problems. So I tried turning off the dp/dt, So someone said that, hey, on the forums online, they said that they try to turn off the DPDT term. How do they do it? Okay, the DPDT term is here. You can insert this by taking this DPDT term out, and apparently for him it worked. Okay, apparently for him it worked. So yeah, when you have this DPDT term, it says that open foam, buoyant pimple foam may have some problems trying to resolve this DPDT term, especially if you have some turbulence involved. So yeah, you have this Courant number problem again. So this solver actually crashes without being able to converge. So yeah, DPDT term, I tried to eliminate that as an issue, but over here you see the Courant number still grows. I don't know why. So yeah, you see that many people actually have these same issues. I was searching online to see if I was the only one. Apparently a lot of people have problems with buoyant pimple foam runs. Okay, so and for those cases, a lot of people did not find their solutions. So I was wondering, hey, is buoyant pimple foam not able to do resolve turbulence? And that seems to, at least at that time, it seems to be the case. Or maybe I'm still missing something. Okay, so I went on to try and find whether was I missing some other aspects of this simulation. For example, this thermal diffusion timescales, which means there is am I not resolving? Is my time scale, the Kolmogorov scale, is it not small enough that I'm not resolving something? Is that why it is causing this instability issue? And I found out that long and short of it, it wasn't the issue. Criteria for that is met. So I try to, okay, let's try something a little easier. I move on from DNS to try LES with a proper LES mesh. Okay, so I try the LES mesh for IDDES case 2. Delta X plus is 40, or I would more accurately say the streamwise. Streamwise mesh size will be that fineness. And I try the Crank-Nicholson time scheme with LES mesh. After 0.15 seconds of simulation time, the simulation blows up. Okay, even this actually blows up at about 0.15 seconds of simulation time when you have this periodic thing. Okay, and more reads online, I found that yes, this buoyant pimple foam velocity oscillations are a very common problem. I think I got this broken link here. Never mind. Okay, and then there was this thesis here. Okay, someone actually also tried to solve this problem in here. So these are some reference cases. We have a heat transfer. So okay, all of these show that buoyant pimple foam does give you some problems with that. The solver seems unstable for an issue. And as I kept reading, I realized something. Actually, Batchelor scales apply to forced convection, not just natural convection. And I was like, oh no. Okay, so that means actually my mesh needs to be made a lot finer. Okay, however, I think from some of these papers online, it says that you only need to refine the mesh in the wall normal direction to suit the Batchelor scales. in the streamwise direction and in the span-wise direction for channel flow, you do not need to worry about that. Okay? So Batchelor scales are Kolmogorov scale divided by the square root of Prandtl number. So for this simulation itself, I'm using a very high Prandtl number fluid, or high enough, about 16 to 20 range. So you do need to take into account the Batchelor scales, and that would easily give you about 16 million cells, which obviously this 8 GB RAM machine cannot run. So I thought of buying a new machine with upgraded RAM. So yeah. However, even then, doing LES, large eddy simulation, the Batchelor scales, or at least the smallest scales of turbulent heat transfer, should be modeled in theory. However, even then, with this coarser mesh, it wasn't able to run. So I kept running IDDES. So was my Batchelor scales, not small enough? Okay, if Batchelor scales were the issue, there are two ways I can actually deal with it. Okay. First thing first. I made a note here that I need a better PC with because I'll be using about 16 million cells. I need a 32 GB RAM machine just to compute it comfortably. All right. So I was thinking of, hey, let me resolve lower my time step and my maximum Coron number from 0.5 to 0.09 just to ensure that the time step can accommodate these Batchelor scales. Alright, so again, this didn't actually work well. That didn't work well. My other way of dealing with this is to use air as the fluid. That air actually has a Prandtl number of less than 1 or 0.71. So the Batchelor scales are actually not as much a concern in this case. So if you use a fluid with Prandtl number close to 1, the Batchelor scales are on the same order of magnitude as the Kolmogorov scales. So even with that, the model blows up. So the solver becomes unstable, it blows up. But anyway, that was an important note to make sure you got to take care of these Batchelor scales as well. That's just something you got to take note for. Prandtl number fluid with Prandtl number, very different from 1, especially high Prandtl number fluid like this oil. Okay, so I suspect that the initial field was a bad field. Bad initial field. Again, I try to change the initial gas. Okay, the initial gas of the fields, that means the temperature, the velocity, pressure field. I try and make it a little bit, I try to map a coarse solution to it. So maybe that works better, or I start from scratch. Both of the times it failed. Okay. So next thing, I suspect that pimple foam in general isn't too well suited for resolving turbulence, LES or DNS, but it seems to run okay with RANS type. So that was my suspicion. Okay, so how unstable is pimple foam? So I took heat transfer out of the equation and I tried to run with pimple foam just without the heat transfer. Okay, so I will stop for now. I will continue this review of what actually the kind of steps I took, and I'll continue in the next video. Thanks for watching. Bye bye.